course, you got all the experiment in 1G until the moment that you deploy the experiment, and even gravel has some elasticity. And so as soon as you go from 1G to 0G, you got all those effects plus some of the vibrations of the actual deployment that affects your gravel, and everything starts to, in our case, it was levitating slowly. But even the first experiment allowed us to understand understand some characteristics, because what happened is that basically the ground became fluffy, on a say. It's very, very porous, extremely porous. And of course, if you add extremely porous material in the ground, then your lander sinks completely. And that's what we saw in the first drop.
We are back with another episode of the Cold Star Project, the podcast about, scaling space companies. And I'm here with Dr. Joan-Pau Sanchez. Thanks for being here.
Thank you very much, and thank you for inviting me.
You bet. So Dr. Sanchez is, he's got a doctorate from the University of Glasgow. He is a lecturer in space engineering at Cranfield University. And those of you who have heard the Florian Gaucher interview will know that Dr. Sanchez here is, well, I won't say you're his boss, but you're what's the word for it?
Supervisor. I was his supervisor while he was here at Cranfield,
right.
Yes.
Right. So I thought that was a really neat connection, and that was, for me, coincidental. I didn't plan that out at a lot. So let's start off with something here that I came across that was interesting. You were one of the first people to publish a near-Earth orbit asteroid map with some ideas about mining them, bringing them in for resource gathering. And this was well before deep space industries and planetary resources were talking about doing that. How did you come up with that as an idea?
Yes, so we have been working on low energy transfers, which means transfers that require very little delta V or capabilities, propulsive capabilities to actually reach different objects in the solar system. And so we realized that many asteroids could be reached with tiny, very small delta Vs. So, and basically, for many of those can be reached much more easily than the moon itself. And so just discussing, we realized of the potential for mining. I mean, there has been talk about mining asteroids for a long, long time, from the very beginning of the space age. And so as a postdoc, that was my first year as a postdoc, one of the first things I wanted to do was to actually check in a statistical approach what is the amount of mass that is available at a given delta V. And terms delta V at the end is equivalent to the energy change, or the energy necessary to reach a place. And so that was the thought there, just understanding what's the promise for asteroid mining, rather than computing particular transfers to particular asteroids, because those might exist or not depending on the launch date, so the actual the date in which you are going to launch. But understanding from a more statistical point of view then allows us to understand if there is actually a potential or potentiality on asteroid mining. Yeah.
Okay, a slightly different approach too to how to get there, and almost more statistical than individual. We're going to pick this specific target. Okay, I'm going to read something from your LinkedIn profile here, which I found interesting, and ask you a question embedded in it. So you had talked about some new rich families of exploitable orbits, which may enable radically new mission applications and services. What are some of these? Why haven't these orbits been used before?
Well, I mean, as we improve our knowledge, the mathematical knowledge on how to describe orbits and compute them, take into account different perturbations and accelerations, then we are able to compute more families of orbits. And with these orbits, meaning periodic orbits, an orbit that closes, or if doesn't close, is close to closing. So it stays on a bounded area, so it remains on a region. And so we are able to compute new families of orbits with improvements on the mathematics of astrodynamics, so the way that we calculate orbits. And so once you are able to compute a new orbit, then you might think about applications for those orbits. And an example could be, for example, recently there has been talks about putting lunar gateway, so a space station in near the moon, in something that is called a near rectilinear halo orbit. So again, this is a halo orbit which has been known for quite a while. But once you increase the energy of this halo orbit, then you reach a new family or subfamily of halo orbits which have a special set of characteristics. And so then you might think about uses of that orbit, and the lunar gateway came up through that. Or the use of near rectilinear orbits came up through this. So that's an example of new rich families or new families. And you can think of many also in orbiting the Earth, for example. If you think about the geostationary ring being overbooked, then you might think about a geostationary ring that is displaced out of the equator, so that like a second floor of the geostationary ring, using low thrust device as a new acceleration. So then you can, using the mathematics to describe these orbits, you can come up with new families of orbits and then their applications. So that's what it means, that sentence there.
Okay, so different orbits have different characteristics. That's an interesting thought. So if we're going to go geostationary, we tend to be further out from the Earth. Okay, what do you think about the current sort of, it's almost a panic about cluttered Earth orbit. I see a lot of social media artwork, infographics and things like that, spreading this idea that suddenly we're going to get into this Kessler syndrome danger situation, which I've had a senior space government official tell me is absolutely not afraid of a Kessler syndrome happening, and I tend to agree. But you know, we are going to be putting up tens of thousands, hundreds of thousands of small sats up there. Is there any risk at all about this, or is it just kind of silly?
No, there is. I mean, so we certainly need to understand, or to make sure that when we deploy new missions, there is an understanding on the potential issues with actually overpopulating a given orbit, and then having issues with regards to space debris. And so we need to make sure that those orbits are, or the use of those orbits is sustainable. And the same with particularly some orbits that are very useful, like not just the geostationary orbit, but also, for example, sun-synchronous orbits. Sun-synchronous orbits are also very much used and overbooked, and so that the risk is in those. It doesn't mean that from today to tomorrow we may have some sort of like the Gravity movie, in which some sort of cascade of impacts that will just make an orbit unusable, but more that we need to make sure that in the future and in the next 10, 20, 30, 40 years, we understand the sustainability of those orbits, and we don't put those orbits on peril. So that's the meaning of that. Yes.
Okay. Let's talk about a new program for you. It's called the Comet Interceptor program, and this is through the ESA. It's something that you're working on. Tell us about that. Yes.
So Comet Interceptor is a new mission. Was selected recently, and it was. End of July, mid last year, 2019. ESA, so the European Space Agency, selected this new mission within their new mission program called FAST mission call. FAST meaning that from selection to launch will be less than 10 years of development. So for this particular mission should be launched in 2028. And so they put this call initially, and so a bunch of I think there were about 20-something submissions, if I don't remember wrongly, 20-something submissions of mission. They call it mission ideas, but now this is not just one page of a guy just writing some crazy stuff about a mission. These are mission proposals with a lot of work behind, of a very large group of scientists and engineers describing how the mission will work and so on. And so our proposal was called Comet Interceptor, which is, and the idea here is that, because one of the characteristics of this mission call is that another mission is a mission called Ariel. Is going to be launched. It's going to be launched. It is the M5, M4 mission. And so the medium-sized mission from ESA is going to be launched to the L2 point. and we are going to be piggyback on that launcher. We are going to be launched to L2, and then we remain there. And then our proposal is to stay there for a while until we discovered a comet, a type of comet that we have not yet visited, which is, those are hyperbolic comets or new comets, new long-period comets, which are the first time that pass through the inner solar system. And so the idea is then to use the propulsion system of the spacecraft while we have remained in L2 and the Sun-Earth L2 for a while to actually reach the comet and then visit it for the first time. By visiting here means very fast flyby on the order of somewhere between 30 to 40, depends on the comet, but it could be up to 70 kilometers per second flyby. And then understanding the differences of these comets, the comets that are the first time that they pass through the inner solar system, with and how they compare with other comets that we have visited, which are comets that have passed through the inner solar system many times. And that will answer many questions about the evolution of comets and so also the evolution of the solar system.
Okay, so you send this vehicle out to Lagrange point. It has to sit there for some period, maintaining some level of power and communication back to Earth. And then it has to power up and do a burn to go somewhere specific after that. How long do you estimate it might have to sit there for? Is this months or years? No,
years, yes. Somewhere between probably 1 to 3 years. That's the thought here. Yes, it requires, so in fact, my specialty is astrodynamics and trajectory design. And particularly things like multi-body problem. And so I can say that, yes, it requires very little delta V to actually being a station kept or keeping a station keeping L2. So it depends on the orbit and depends on many things, but in the order of 10 to 20 meters per second is certainly plenty, which is very little. And one thing that often I see people confused about is the fact that they say or they think that the L2 is unstable. Typically, it's well known that the L2 and orbits around L2 are unstable, and therefore, as if this meant that it requires a lot of delta V again, so the propulsive capability, in order to be kept, a spacecraft to be kept there. But in reality, we require less delta V to be kept at L2 than for a geostationary spacecraft to be kept at the geostationary ring in their own slots of the geostationary ring. And so the issue with the instability of the L2 means that if you have, say, a failure in your propulsion system and you cannot do the station keeping, then it means that you actually drift away and you go somewhere else completely different, so you don't stay there. That's the main thing with instability. Okay.
Other than the instability possible issue there, are there any other problems that could come up as it sits there for 1 to 3 years?
No, apart from the station keeping, well, and potential failures of different things, but it should be, not specific with this mission. So waiting there for a number of years shouldn't be a big problem. One of the issues is going to be to decide to what comet and when we're going to be actually departing, because you only have one shot, so you need to decide well. So you might have a comet coming up, and you may be tempted to wait a little bit longer or just to go ahead with this one. So that's it's going to be one of the challenges of the mission, just to be sure that we decide or we pick the best option. And another very interesting thing of this mission is that we might have a chance also to fly an interstellar object. So there have been so far 2 interstellar objects discovered, and so with LSST, the new survey and telescope, we might discover some one or so every year statistically, and so we might have a chance to actually have a good target to visit, so a good interstellar object to visit, and that's a bonus for the mission. Eventually, it could be the first mission going to an interstellar object. Okay, so you will do a flyby with this. You will not land on it. What sort of information do you hope to pull? And is this is going to be transmitted back to Earth to a ground station, I take it? Yes. So actually, another of the novelties of this mission is that it's not just one spacecraft; it's three spacecrafts.
Mm.
So it's going to carry three spacecraft, a mother craft and two daughter crafts, that we call them. One is provided and designed by JAXA, the Japanese Space Agency, and the other two are provided and operated by ESA, the European Space Agency. And so each of the spacecraft will, once we are close enough to the comet, will separate and will follow slightly different paths. And they will then be the first, it's going to be the first mission that takes simultaneous measurements of the different characteristics of a comet simultaneously over the flyby in different positions. In this way, we will be able to understand the physics behind the evolution of the comet and the evolution of the comet much better. And well, we carry a bunch of different payloads, scientific payload, in the different spacecrafts, from obviously cameras to magnetometers, etc. So yes, so one of the nice things of the mission is that it's going to be three different spacecraft flying at the same time. But again, we cannot land, because to land it will represent massive delta V, but impossible because these objects are moving very fast. But we can pass very fast around there. So that's what we are going to do.
Okay. And what kind of propulsion method are you thinking of?
Well, it keeps on changing. Initially, it was chemical, then it went to low thrust, now it's back to chemical. Probably, so now ESA, so now we are what is called a phase 0. So it's the beginning of when ESA has selected the mission, and we start we're starting designing properly the mission. Mid-2020, we will, the phase A will start, in which then you start designing in detail each part of the mission. And in there, we will start finalizing the decisions of what sort of propulsion system we are going to use. The chemical propulsion system is seen as suitable and the low performance of the two options, but because one of the issues also with this class of the mission is that this is relatively low cost compared with other interplanetary missions that ESA has launched. The budget for this mission is 150 million euros, so it's quite little for an interplanetary mission. I think that a medium class in ESA is about 500 million, so it's substantially smaller than a medium class. Although here we don't need to pay for the launch because it's provided anyway for the other mission, bigger mission. So yeah, at the moment it's chemical propulsion, but it might go back to low thrust or even hybrid propulsion, so combining the benefit of the two. So we'll see how it evolves the design.
I mean, this is a long-term thing here. It's 8 years until the planned launch, assuming there's no delays or anything like that.
Yes.
And it's got to travel out to L2 and then wait a couple years and then go out to the object, which could take much more time as well, and then give you the data back. And so we're looking at 15 years maybe?
Yeah, potentially the whole mission lifetime, yes. But it's standard with many missions from the beginning, because this was selected last year, so we are in phase 0. So that's the very, very beginning of mission lifetime, in which we are in the preliminary design phase of the mission. And yes, it takes many, many years. Rosetta was a much longer mission, and well, it took very, very long. The same with Bepi Colombo and many other ESA missions, and the same happens with NASA missions. So yes, typical for an interplanetary mission. It takes many, many years.
Right.
The conceptual design, the conceptual thought of the mission to the actual end of life of the mission.
So you have to wait quite a long time to find the results of your baby. This is Jason Kanigan from Cold Star Tech, and I'm excited to share with you a new offer from Cold Star that we are bringing out to help both space founders and venture capitalists who fund space companies. And it's on 2 levels. The lower level is a VC who is looking at possibly funding a space company, but they just don't get it. Right? And a lot of tech founders want to come out and create some sort of technical capability, but they do not understand business. And so you'll look and you'll go, where's the customer here? Where's the business model? And they'll go, huh? But I want to make rockets or something, right? And it's really cool. Well, that, as we know from the dot-com era, is not a viable business model. And so you bring us in. We've got great technical expertise on the space side, folks who have done this sort of assessment before, like our technical engineering advisor, Dr. Rick Fleeter, myself in the process engineering field, plenty of other people with brains to look at this problem so that you don't have to blow your brains out trying to figure out how to make this work. And on the company side, it's a benefit for them because we will show them the roadmap to how you're going to get funded, how you will want to fund them, what changes to make to get VCs excited about putting money in. And so that's good for you. Right? The second level is at a deeper and higher level at the same time. It is for venture capitalists who have given a seed round to a company, a space company, and that has gone on for a little while, 6 months, a year, something like that. And it is time, as COVID has made it, to double down or get out. Those are pretty much the choices, right? It's time to invest further in a thing we already know, which seems to be the direction VCs are going in right now. They don't seem to want to look at new things or stop, just kill the project. And so the good news is, in that situation, there's a lot more going on. There's more meat for cold star experts to get in and analyze, right? You're going to have processes in place, whether they know it or not. We'll be able to flowchart those and maybe accurately document them for the first time so we can get some kind of value chain going in the organization. We'll be able to test whether the leadership is the right group of people or whether you're missing something, the strategic direction, the business model, all this stuff. So if this sounds interesting to you, reach out to us. You can email me at jason@coldstartech.com or just connect with me and message me on LinkedIn. That's probably the best way to do it. And I am excited to talk to you. The kind of transformation that we're able to offer here is beyond anything you'll see out there. And as a VC, this will save you so much time and energy, right? Like if you're a VC and you've got 100 companies to look at, you've got 3 days a year to look at each one, maybe, right? That's not really good enough, is it? Wouldn't it be better to have experienced, expert space people who understand space, right? Look at this investment and tell you, here's a grade, right? Here are several grade areas. Is this thing ready to pour gasoline on the fire, or is it just going to go up in smoke? This is Jason Kanigan from Cold Star Tech. Let's get back to the interview. Well, let's move from a flyby to actual landing on things. You and Florian Gauche worked on a project about landing CubeSats on asteroids. Tell us about that. I'm interested in your point of view on this project.
Yes, so one of the questions we had, and that came from previous work of mine, was if we were, because one of the things we were doing was computing ballistic landing opportunities for asteroid exploration. By ballistic means that basically you can have a motorcraft orbiting at a safe distance with the asteroid. And this is key because often when you reach an asteroid, you don't really know the shape and the gravity that you will find there, the accelerations you will find when you're close. You are far from the Earth, so you cannot really control by, say, joystick. So you're going to have a controller just understanding what's going on at every single time. And so often you spend many months just flying in information with the asteroid from very far away. and you would like to get very close to the asteroid in order to start understanding the asteroid, understanding the gravity and so on. And so one potential solution for this issue in order to speed up this process would be to deploy some cheap spacecraft, you could say, for example, a CubeSat. And then we were investigating how we could actually land a CubeSat without control, without propulsion system, so that you basically could just deploy a scientific payload. And then we realized that there were ways to actually land in asteroids that allowed us to actually touch down at very slow velocities in the order of tens centimeters per second, which wouldn't jeopardize the actual integrity of the payload at touchdown. But the main issue was the amount of energy that you would dissipate at touchdown. Because if you don't dissipate much energy, it could be that you bounce off the system completely and you don't come back, or you bounce around and you end up on a shaded area on the asteroid. And so that was a critical. And so that's why we thought about the experiment that you already discussed with Florian, to have a little bit more understanding about what's going on this touchdown. So how is the interaction between the lander and the surface on an asteroid.
Okay, and you worked at a facility I was reading about here. This is new to me, the ZARM Drop Tower in Bremen, ZARM. Tell us about that.
Yeah, so this is a tower, basically. It's about 150 meters, but I don't remember exactly, but it's about that tall. And basically it's a tube which gets, it's when just before launching the experiment, it gets in vacuum, so that in order not to have much air drag, and then you deploy from the very top a capsule where you got the experiment and everything, and then it allows you to give about 4.5 seconds of microgravity conditions, a very good quality microgravity conditions in the order of 10 to the power of -6 Gs, which is much better than what you can get generally on parabolic flight, which is the other way to get microgravity conditions. But of course, then the capsule reaches the ground and you need to slow it down somehow. Yes, and so in ZARM, then at the very bottom, you have a kind of a pool of pellets, basically, that allows you to slow down the capsule, but it's still everything inside the experiment needs to survive somewhere between 25 Gs to 50 Gs of deceleration.
Okay, and is this where you notice things like the consistency of your fake asteroid didn't quite stay together the way that you thought it would?
Yes, so yes, initially one of the issues was that, of course, you got all the experiment in 1G until the moment that you deploy the experiment, and even gravel has some elasticity, and so as soon as you go from 1G to 0G, you got all those effects plus some of the vibrations of the actual deployment that affects your gravel, and everything starts to, in our case, it was levitating slowly. But even the first experiment allowed us to understand some characteristics, because what happened is that basically the ground became fluffy, on a sense, very, very porous, extremely porous. And of course, if you had extremely porous material in the ground, then your lander sinks completely. And that's what we saw in the first drop, for example. So you can, and then also with what we saw in the following drops, we had 7 in total. You can start building your intuitive understanding of what are the effects when you touch down, and it gives you a lot of insight on what's going to happen, and what has happened with Philae, the Rosetta lander, and the touchdowns also from Hayabusa. So yeah, it was a very successful experiment altogether, even the unsuccessful attempt.
Right. Well, I love hearing about all these different studies all over the world. There's folks making beds of lunar material to simulate what that regolith is going to be like, and this is just as useful. So I'm curious how you get this knowledge out. The two of you were working on your paper for submitting it, I guess, for journal publication. Tell us about that process and where you're at. I mean, as far as I know, this ended like a day or two ago.
Yes, yeah, we submitted recently. I think it was last week. Yes. So basically, the way to disseminate the results. We have gone to different conferences and we have presented the results. Also, I mean, the people who are working on these particular problems, they saw our work, and we actually got contacted by some of the people, for example, working with Mascot lander that was deployed by Hayabusa 2, just to understand a little bit more our results and share that knowledge. And we continued working on that document, the final description of all the experiment and the results, and we submitted recently to Arte Astronautica. Now, what's going to happen is that this gets peer review, so reviewed by 2 to 3 reviewers, which are going to be also scientists working on the field, and then we receive their reviews on an anonymous form, so we don't know who they are, and then we need to reach sufficient quality of standard of quality of the publication before we get published. But I'm confident that the paper is well written and has very good results. So should be
right. Okay, and so with this study, you've learned quite a bit about microgravity and how to land a small satellite on an asteroid, which is a weird thing, right? It's not a boulder flying through space. I think the general public needs to understand it's often just a mashed together, held together by low gravity forces, mishmash of different materials in that. And so you've learned, okay, if we come in and we don't know how to slow down, or we don't hit too or hard enough, the thing will just bounce off and we'll either fly back out into space or land in a place that's hundreds of meters away from where we wanted to, and it's not useful for what we wanted to find out. What is the next step? Is there a next step in research on this?
Yes. So now at Cranfield, for example, we are working on guidance, navigation, and control algorithms for the lander, potential CubeSat landing, which should be able to interpret or understand its own position, and then understanding what's the path that is following, and doing some prediction of where it's gonna fall, and potentially then either transmitting this information to the model craft or even taking some decisions about some controls. But the controls is still not, because with such a small gravity, so you are in microgravity conditions again, any small error on the propulsion system might not be might be difficult then to counteract. So it is an issue. That's why we were trying to do ballistic landings, so just that you drop it. But one of the things that is needed for the future of exploration of asteroids and just the future of interplanetary missions in general is autonomy. Autonomy meaning the capability of the spacecraft to understand its position, its velocity, and take decisions about it. So if it's not on the right path, then perform some correction maneuvers. Up to now, all the interplanetary missions had very, very little autonomy. So typically the autonomy that you had was more on the, for example, the landing of a lander in Mars that should have to be autonomous because of obvious reasons, because you cannot really control it on those minutes that is falling and so on. But and you can see the challenges. So many landers have actually crashed rather than land because of that lack of because of the difficulty of having an autonomous vehicle that is able to respond well. So the same with asteroids, asteroid exploration. We have had very little autonomy on asteroid exploration, and especially if you want to have very low-cost missions like CubeSats flying, you might need some autonomy. And Comet Interceptor, for example, we might have some autonomy in some of the daughter crafts. So the small spacecraft that will accompany the main mother craft of Comet Interceptor, and that will be one of the first times for such a mission as well.
Right. Yeah, and this is an issue I've known about and I've been writing about for maybe 5 years. You're not going to have a human pilot out there. That's very unlikely, and the distances are so long. Again, I'm saying this for the general listener. You cannot signal the thing to change direction or something in time as it's flying towards a comet or an asteroid or something like that. It has to be able to make that decision itself. And so in order to do that, it needs a lot of data. It needs a good simulator. It needs to understand the math very well about what's going on around it and be able to do some predictions and come up with the right course of action. Let's talk a little bit about algorithms here. There's a thing called the traveling salesperson problem in active debris removal and servicing of satellites. I guess you're not going to service a CubeSat, but maybe larger. What is that traveling salesperson problem? Let's let this be our education portion.
Yeah. So, well, the traveling salesperson problem is the problem of is an optimization problem. Is a paradigm in optimization, a classic optimization problem in which you have a salesman that needs to go to a group of cities, and you need to find, so the salesman needs to find the optimal path to minimize the total distance traveled. So you can only go to one city once, and then you need to link city after city. And then the problem requires you to find out which is the minimum distant path, so the way to go through all of the cities with a minimum distance. Up to now in space, I mean, this problem by itself didn't have much to do with space, because when you were launching a spacecraft, you were going to one single place, so either one single planet or one single asteroid or one single orbit and staying there. So it didn't have much to do with, so space trajectory design didn't have much to do with traveling salesman problem. But in fact, with the new missions now, some missions are getting a little bit more daring, and so we are considering doing different approaches. So, for example, recently we also submitted a mission proposal in ESA, and previous to that there was also a mission proposal for NASA, which was similar, which was to send a spacecraft that instead of going to one single asteroid, goes to 10 or more. And so there you got the same problem. So then is when you build this, the need to, in a space, also to find a way to minimize the distance. In this case, you don't minimize the distance because you don't care that much the distance and when you are traveling around the solar system, but more the delta V, so the total cost of propellant. And it's a bit more complicated in space, because here the asteroids that you might want to visit are moving actually. So cities do not move, but the asteroids do. So it's a bit more complicated. And there are other similar problems in space now. Like, for example, I'm going to several debris and to remove them in LEO or GEO, or going to several spacecraft to actually to do on-orbit servicing. So so that's one of, in fact, we have now running a project together with Airbus Defense and Space of investigating efficient algorithms to come up with solutions for this space-related travel and salesman problem for different types of problems. And so yes, now it's a relevant. So it's very relevant to investigate ways to find out the best ways to design trajectories that go to many places in space.
Okay, and do you think that these algorithms can be developed without the help of supercomputers?
Yeah, well, that's the key thing there, because more than you need to find ways to compute feasible solutions, good solutions, very fast.
Mm-hmm.
So it's different than to find the very optimal solution. For a space mission design, you might not, or you might want to find the very optimal, the global optimal, but that might not be that relevant. You said before that a launch might be delayed. And so if your mission relies on one single opportunity that requires one single launch opportunity, then you have an issue there. You are very likely to fail, and so the whole mission might not be developed because it is seen as very risky. So what you really want when you're doing preliminary mission design is to come up with many different solutions as best as possible and in a very fast way, because later on the space system engineers might actually change some of the parameters of the mission, like for example the amount of propellant that you have, or the capabilities of your thrust, some requirements with regards the communications and the communications operations and so on. So it might change something, and you will need to run again the same search and find new trajectories. And so what you want to have is efficient algorithms that allows you to find many solutions as fast as possible. And you don't want to have, ideally, you don't want to use supercomputers. You want to use standard, perhaps some clusters, some good set of power stations, but not a massive supercomputer. Yes.
Okay. How far away are we from that, or is that a reality today?
Well, you can have good solutions, and generally you have. For example, there is a very interesting exercise that is run every year and something, which is the GTOC, which stands for Global Trajectory Optimization Contest or Competition, which is sort of a American's cap of optimization, trajectory optimization, in which every so often there is a problem that is advertised, and then a bunch of different teams try to come up with the best solution. and then the winner organizes the next event, which generally happens 1 year after. And there has been many of these sort of problems that have been proposed before, and there were many interesting solutions and very, very, very good solutions that were submitted. So we do have the capability to come up with good solutions, but there is always room for improvement, especially if you want to be able to have very flexible algorithms, so algorithms that can tackle as many different problems as possible. So in that regard, yes, there is a lot of research to be done still.
Okay. Well, let's finish up then with this question. What are you looking for, Dr. Sanchez? What is the future for you? What is of interest to you?
Well, because I have many interests, I hope to continue having a lot of fun doing space research, which is basically why I'm in the business or in academia. I just have a lot of fun doing all these things. I hope that Cranfield and my research group continues developing the GNC, the Guidance, Navigation and Control for small spacecrafts. And I hope to have the opportunity to launch or to be involved in a mission, perhaps Comet Interceptor or a smaller CubeSat-rated missions, which requires to actually put on board these guidance and navigation algorithms and actually see them working and hopefully working correctly. So that's what I hope and hoping to see in the future.
All right. And if anyone wants to get in touch with you, what's the best way to do that?
Email, the university email, or LinkedIn. I'm easy to find in LinkedIn as well. So yes, probably these two are the best.
All right, Dr. Joan-Pau Sanchez, thanks for being here today.
Thank you again for inviting me. It has been a pleasure.
This is Jason Kanigan from Cold Star Tech. Thanks a lot for listening to this episode. I hope you enjoyed it. If you do want to get email notifications of upcoming episodes or episodes that have just been released, and maybe a little news sprinkled in here and there, you can sign up for email notifications at coldstartech.com/MSB. That's short for Make Space Boring. That's another little show that I do. It's once, twice, 3 times a week, something like that. Anytime there's news or an update on who I'm meeting and what I'm studying in the space field. So you can go check that out. On the YouTube channel, I can do something that I cannot do on Anchor for the audio only side of things. The YouTube channel allows me to have playlists, and so you might want to go to the channel, the Cold Star Tech channel, and check out those playlists, because you will find you can go down a rabbit hole basically into several areas like space law and policy, smallsats, and I think that's a lot easier than trying to scroll through 130 episodes or something like that, looking for the thing that you want. So I recommend going and checking that out. And remember, if you're ready to take your space business to the next level, or you're a VC looking for deep and very valuable insight into a space company you're looking at investing in or investing further in, come and talk to us. Thanks for listening.